This is part 2 of our lesson on equations of polynomial and rational functions. So in question number 1, we had a rational function. I can tell because it had asymptotes. We used the x-intercepts and the asymptotes to help us figure out our equation. This one is a polynomial function. How do I know it's a polynomial function? It doesn't have any asymptotes. How do I know there isn't an asymptote at 3? Well, if there was a vertical asymptote, there would have to be curve on the other side of it. So there is only one piece of curve, so I know that there aren't any asymptotes. So when I go to do the equation for this one, it's a little bit easier because there's no denominator. So the denominator is where the vertical asymptotes come from. So I only need to worry about the numerator, which is where the x-intercepts come from. When I look at this graph, I see that it has x-intercepts at -4, -2, +1, and +2. So I am going to start by listing my x-intercepts and trying to figure out what the bracket would be that gave me those x-intercepts. So I have x equals -4, x equals -2, x equals +1, and x equals +2. The x equals -4, I would add 4 to get x plus 4 equals 0. So one of my brackets will be x plus 4. X equals -2, I would add 2 to get x plus 2 equals 0. So one of my brackets is x plus 2. X equals 1, I would subtract 1 to get x take away 1 equals 0. So x minus 1 is one of my brackets. And then finally, I would subtract 2 from the x equals 2 to get the bracket x minus 2. So we have brackets x plus 4, x plus 2, x minus 1, and x minus 2. I know there's no denominator, so I can just take my equation and start building. So I could do f of x equals, I could do b of x equals because this is question B, or I'm just going to write y equals. So I'm going to have a bracket x plus 4, x plus 2, x minus 1, and x minus 2. Once I have all of the brackets in place, I want to see if any of them have an exponent on them. So since these are x-intercepts, I would notice that it had an exponent if it was either a critical point or an inflection point at that intercept. So if I look at -4, I notice that the curve just passes straight through, which tells me there is no exponent on the x plus 4. At x plus 2, I notice that it does that little wiggle, which tells me there's an inflection point there. So we get inflection points when we have exponents that are odd numbers, like 3, 5, 7, or 9. I'm going to say this has a power of 3. If it was a power of 5 or 7 or 9, you would notice that it would be a lot flatter when it hits here. They're really quite noticeable when you have a higher exponent. All right, the next one at +1, just passes through. So I know that there's no exponent there. And then the one at 2 bounces back. So there's a critical point there at that x-intercept, which tells me that it has a power of 2 or 4 or 6 or 8. I am going to say that I think that it's a square. The higher the exponent is, the flatter it's going to be at that point. So it usually is quite noticeable if there's a higher exponent. So I usually tend to say if I see a critical point, it's a square, and if I see an inflection point, it's a cube. Now there is no denominator because there are no asymptotes. This is not a rational function. All I need to do now is see whether or not there is a number in front. I am temporarily going to put k there. Now I can tell by looking at my graph and looking at the ends that the right-hand side is pointing up and the left-hand side is pointing down. So that does tell me that this should be a positive leading coefficient. So k is probably a positive number, but I would like to actually know what the number is. So I'm going to look at the marked point. This time the marked point is the y-intercept. It is the point 0 and -4. So we are going to use 0 for x, -4 for y, and sub those numbers in. So for y, I'm going to put -4 equals k, that's what we're trying to find, and then x, so 0 plus 4, times x, that's another 0 plus 2, and that's cubed, and then 0 minus 1, and then 0 minus 2 squared. Now you are welcome if you want to do it all at once on your calculator, but I think I'm going to do it in some smaller steps. So I'm going to leave the -4, I'm going to leave the k. 0 plus 4 is 4. 0 plus 2 is 2, and 2 to the power of 3 is 8. 0 take away 1 is -1, and then 0 take away 2 is -2. -2 squared is +4. All right, I am going to multiply those numbers together. So I have -4 equals k times, and I'm going to use my calculator to help me out. So 4 times 8 times -1 times 4. And I end up with -128. A common mistake people make, instead of doing k times -128, they write k minus 128. This is not subtraction, it is multiplication. So if I want to solve for k, I would need to finish by dividing both sides by -128. All right. Does -4 divide nicely by -128? Well, I guess it depends on your definition of nicely. If you would like to write it as 0.03125, you are welcome to do that, but you do need to include all of the decimals. You are not allowed to round. So if you wanted to write every single one of those down, that's fine. I think I would prefer to leave it as a fraction. If it was something easy like 0.5 or 0.25, I would probably write it as a decimal, but I don't want to write all 5 of those down. So I'm wondering if 4 over 128 would reduce. So I do know that a negative divided by a negative makes a positive, so my answer is going to be positive. I'm going to try dividing by 4. 128 divided by 4 is 32, and 4 divided by 4 is 1, so I believe this is going to be the fraction 1 over 32. So that means in front of this equation is the fraction 1 over 32. What that would do is compress my graph, so I used that number to squish down my critical points so that they weren't as high, because otherwise you wouldn't be able to see them on the graph. So now that I have my k and I know what all my brackets and exponents are, I'm going to write my final answer. I'm going to say, therefore, y equals 1 over 32 times x plus 4 times x plus 2 squared, cubed, not squared, times x minus 1 times x minus 2 squared. All right, so that's what you need to know about how to find the equation of a polynomial and rational function.